This is a Kepler triangle. As a right-angled triangle, it conforms to the usual Pythagorean rules in that the squares of the two smaller sides equals the square of the longest side. In addition, the Kepler triangle has several unique properties. The base of the triangle, the adjacent, starts with the value of 1. The opposite is the adjacent times the square root of 5. The hypotenuse is then the opposite times the square root of 5. The hypotenuse is also the adjacent times 5. Another aspect of phi itself is that 5 plus 1 is the same as phi squared. The most significant element here is the square root of phi, in that the adjacent multiplied by the square root of phi is the opposite, and then the opposite multiplied by the square root of phi again is the hypotenuse, in this case phi. We can scale the Kepler triangle up or down as we wish. We can do this by simply increasing or decreasing the value in the adjacent. Here, this is the actual Kepler triangle, that's 1, and we can scale it up by 2 or 3, or this time scaled down by 0.5. We then apply the same rules of multiplying the adjacent by the square root of phi and then the opposite by the square root of phi. A square with an inscribed circle such that the circle touches the sides of the square is a squircle. Squircles have a very unique property in that they can unfurl and become scaled versions of a Kepler's triangle. The perimeter of the square becomes the opposite side in the Kepler triangle, and the circumference becomes the adjacent. Above the squircle with its corresponding Kepler triangle, the sides of the square are the square root of phi divided by 4. Therefore, when we multiply by the 4 sides, we have the square root of phi. In the next example, the side of the square is 1, therefore the perimeter is 4. The perimeter of the square morphs into the opposite in the scaled Kepler triangle. As the side of the square is 1, then the diameter of the circle inside the square is 1. The circumference is pi times the diameter, so pi times 1 is pi, and the circumference from the squircle becomes the adjacent in the Kepler triangle. As mentioned, the hypotenuse is the adjacent times phi, therefore pi times phi. In this table above, we can see the first example is the squircle itself and the actual Kepler triangle. The side is the square root of phi over 4, which makes the perimeter the square root of phi. This becomes the opposite in the Kepler triangle. The example below is a scaled up version by 4 over the square root of phi of the actual Kepler triangle. In the table, we see the scaled version to show pi as 3.1446 or 4 over the square root of phi. From the geometrical relationship in the diagram above, we know that the circle circumference and the adjacent in the Kepler triangle are actually pi. This seemingly suggests that pi equals 4 over the square root of phi. We know that Kepler triangles are scalable. We know that the squircles are scalable and that the squircles morph into scaled Kepler triangles. We know that the example in the table is a scaled up version of both the squircle and the Kepler triangle. Therefore, the values are correct. The geometric example proves that when the square in a squircle has 1 for the side and 4 for the perimeter, then the circle inside must be pi. The geometry proves that the circle circumference is pi. The math in the table proves that that value is 4 over the square root of phi. You can also look at this in another way. The scaled Kepler triangle has an adjacent of pi, opposite of 4, and hypotenuse of pi times phi. Actual Kepler triangle is 1, square root of phi for the opposite, and phi for hypotenuse. For the hypotenuse, we divide phi times pi by phi. The phi's cancel out, leaving pi. For adjacent, we divide pi by 1 to get pi. So the missing value here for the opposite of 4 over the square root of phi can only be pi. We can also do the algebra. In this case, we keep the 4 squared to the left of the equal sign such that the opposite squared equals the hypotenuse squared minus the adjacent squared. Above we have 4 squared equals pi times phi squared minus pi squared. We take pi squared out and then we have 16 equals pi squared times phi squared minus 1. We solve for pi squared and have pi squared equals 16 divided by phi squared minus 1. That becomes 16 over phi. Then we take the square root from both sides and we have pi equals 4 over the square root of phi. We can also test the hypothesis using the actual values associated with pi. Above we have used the standard value of pi. The calculated version, adding the adjacent squared to the opposite squared, gives a sum slightly more than pi times phi squared. In this example, I've used the value of pi generated from 4 over the square root of phi, and there is no difference in summing the two sides with calculating the hypotenuse with pi times phi squared. Several methods have been used here to calculate pi, and all support pi as 4 over the square root of phi.